Now we'll discuss about simple harmonic motion. About SHM we can state it is a special type of oscillation in which during oscillation the acceleration of particle is directly proportional to the displacement of particle from its mean position. As we know well that during oscillation always acceleration is acting towards the mean position, and if it is directly proportional to the displacement of particle from mean position, that this particular oscillation which follows the rule can be regarded as simple harmonic motion. Say if a particle is oscillating about a given mean position with an amplitude, say mean position is x equals to 0 and extreme positions are at x equals to plus a and x equals to minus a being the amplitude of oscillation. In this situation, when say the particle is at a distance x from mean position and it is experiencing a restoring acceleration a, which is acting towards the mean position, and if a is directly proportional to x, negative sign is just indicating that a is acting opposite to the displacement. Then this is the situation we can state that the particle is executing simple harmonic motion. There are some other conditions also which will favor. Let's also visualize the other conditions which will favor an oscillation to be SHM. Some other condition we can also discuss. For favor of an oscillation to be SHM, the most prime condition about it is oscillation amplitude to be very small. In most of cases, if oscillation amplitude is very small, even if the previous rule is not being followed directly, it can be imposed. Let's have an analysis for this. Like if a particle is executing oscillation in such a way that at a displacement x, its acceleration is given as this c1x plus c2x square directed towards the mean position. Obviously, as in this situation, acceleration is not directly proportional to x. There is a term of x square is also there in acceleration, so we cannot directly call it SHM. But if a is very small, where a being the amplitude, like mean position is at x equal to 0 and extreme positions are at x equals to plus a and x equals to minus a. In this situation, if a is very small, we can state that displacement of particle, which is always less than or equal to its amplitude, will also be very small. And if x is very small, the higher order terms for x can be ignored. And here we can approximate it as a is equals to minus c1x, which can be taken as the basic condition for an oscillation to be SHM. So this oscillation in which acceleration depends on x as well as x square can also be taken as SHM if amplitude of oscillation is very small. Similarly, there are many other cases in which we can analyze, like if a is given as not a polynomial function of x, it is given as say sine of c1x. Again here acceleration depends on a sinusoidal function of x, not as a direct relationship between acceleration and x exists. Then also we can state for a to be small, or we can use acceleration as approximately minus c1x, as we can write for a small theta, sin theta can be approximated as theta. So here also we can see this sinusoidal function transform into the function which we require for the particle's oscillation to be SHM. So we can state if amplitude is very small, in many cases even if oscillation is not directly given as a proportional function of x, it can be transformed and can be regarded approximately as SHM. Another condition which is sometimes useful is oscillation of particle should be in a straight line. This is not a very useful and very important condition, but sometimes it happens that if even a particle is moving in a curve, then for a small displacement, if amplitude is very small, the particle's motion can be regarded as a straight line. So we can ignore the centripetal oscillation acting on the particle and it can be directly analyzed as SHM. Later we are going to discuss about some facts related to this condition. But this first condition is quite useful and important, which we are going to use very frequently.